The amount of product we get, if the reaction is perfect, is called the theoretical yield. We find it simply by calculating, because we know how much reactant we put into the reaction. We're able to calculate by simple stoichiometric calculations how much yield, that is, how much product, we should get. Now, if we actually do the reaction and measure the actual yield, that is, separate a particular product, weigh it, let's say, what we're going to find is that this amount that we actually get is going to be less than the theoretical yield. That is, the percent yield can never be greater than 100%. It's kind of like a batter in baseball can't have a batting average greater than 1,000. That's as high as it can go. In basketball, a free throw shooter can't have a free throw percentage greater than 100%. The percent yield is actually something very simple. It's the amount that you do get divided by the amount that you should have gotten if you were perfect, put into a percentage form. If you've ever calculated your percent in a class or your percentage on a test, it is the actual number of points that you earned divided by the theoretical number of points that you could have earned if you'd been perfect. Let's try an example problem here. We're given an equation. We're going to need to check and see if it's balanced. We're given the amounts of two reactants, which right away means that we're going to have to use some of the limiting reactant ideas that we've covered in previous lessons. And we want to calculate, you can see on the right side, the number of grams of this product, which has the name zinc oxide, assuming that we have 81% yield. In other words, we're going to calculate the amount of zinc oxide that we should get if the reaction goes perfectly. But then we're told that the reaction isn't 100% perfect, it's only 81% perfect. So we're going to have to take that into account when we determine the actual mass of zinc oxide that's produced. Okay, let's check and see if this is balanced. I'm seeing on the left 1 zinc, on the right 1 zinc, on the left 1 sulfur, on the right 1 sulfur, on the left 2 oxygen atoms, and on the right 3 oxygen atoms. I trust that if I gave you enough time you could balance that. There it is, correctly balanced. We know we're going to have to do the limiting reactant process on this, so let's do that. We're going to take each of the amounts of reactants and we're going to convert them into moles. The molar mass of zinc sulfide is 97.5 grams, which means the number of moles of zinc sulfide that we have is 1.026. We're going to do the same thing with grams of oxygen. The molar mass of O2 is 32. 100 divided by 32, 3.125 moles of O2. Again, whenever I do limiting reactant problems, I like to write the word have under the number of moles. The next step in the limiting reactant procedure that I use is to divide each of the number of moles by the respective coefficients in the equation. On the reactant side, you can see at the top of the screen in the left, we've got a coefficient of 2 in front of the zinc sulfide, and in front of the oxygen a coefficient of 3. If we divide each of those numbers of moles by their coefficients, we get these numbers. The smaller of those results indicates which of those is the limiting reactant. Now, we weren't asked to find the limiting reactant, but we know that we need to find the limiting reactant because the amount of product is based on the limiting reactant. So let's calculate the number of grams of zinc oxide that we should get in a perfect world. And to do that, we're going to start at moles of zinc sulfide, and we're going to go over to moles of zinc oxide, and then up to grams of zinc oxide. So we're going to start with the limiting reactant. Here we go. 1.026 moles of zinc sulfide. We have 2 bridges to cross, so we need 2 conversion factors. The first bridge, which I'm highlighting with my laser pointer right now, requires us to use the coefficients in the balanced equation for those two substances. For the zinc sulfide, we see a coefficient of 2. For the zinc oxide, we also see a coefficient of 2. So I'm going to go ahead and put the 2's in there. You could put 1's if you wanted, but just to be consistent, I'll put 2's in there. Moles of zinc sulfide cancel, and then we need to convert between moles of zinc oxide and grams of zinc oxide using the periodic table. Check it out. The molar mass of zinc is 65.4. The molar mass of oxygen is 16. There's one of each of those in that formula. Add them up, you get 81.4. Moles of zinc oxide cancel, and we can calculate the grams of zinc oxide that we would get if the reaction were perfect. This is analogous to the number of points that you would have if you got every question right on a test. But if you look in the upper right corner of this slide, we are only 81% perfect. And for that reason, we need to take 83.5 times 0.81, and we're going to round to two significant figures because, again, if you look in the upper right, notice that 81%, which is what we used in our calculation at the end, only has two significant figures, even though these other quantities have three that we were given. So we want to round to 2.